Very good afternoon to one and all. And I, on behalf of the National Academy of Sciences India Delhi chapter and the Dayal Upadhyaya College, University of Delhi, I would like to welcome our esteemed guest for today, Professor Reinhard Genzel, Nobel Laureate in Physics for the year 2020, and who is with the Max Planck Institute for Extraterrestrial Physics, Germany. This particular special public webinar is part of an year-long series which we have been hosting ever since the pandemic started, that is the year March 2020 onwards. And this whole program, which we are organizing various public lectures, workshops, training programs for the school students, undergraduate students, is part of the Science Promotion Initiative of the NASI Delhi chapter and the host institute, Deen Dayal Upadhyaya College. Before inviting Professor Genzel to deliver his talk, I would like to welcome Professor Anurag Sharma and request him to please apprise Professor Genzel and all the attendees about the NASI Delhi chapter. Over to you, sir.
Okay, thank you, Manoj. Good afternoon to everybody, and probably good morning to Professor Genzel. On behalf of the Delhi chapter of the National Academy of Sciences India, which is called NASI in short, and on my own personal behalf, it's a great pleasure to welcome Professor Dr. Reinhard Genzel of Max Planck Institute of Terrestrial Physics at Garching, Germany. National Academy of Sciences in India, NASI, is the first science academy which was established in India in 1930 by Professor Meghnad Saha, who's probably well known to the physics community, particularly space physics community. The academy has major focus on science and society, taking science to and its benefits to society, particularly to rural and tribal areas and to school children, and also undergraduates and postgraduates. In its outreach activities, NASI is helped by its 21 chapters across the country. Delhi is one such chapter, and Delhi takes pride in being one of the most active chapters among all the 21. Last year, in the shadow of pandemic, and which of course continues this year also so far, the chapter organized a large number of online activities for UG and PG students. Something like 160 lectures were organized, like the one today, which continues in the series. Special programs were also organized for women scientists. Lecture and workshops to help UG and PG students with their curriculum was also organized, and so on. I mean, so a large number of activities were done. In the current year also, we are planning major initiatives on similar lines. And thus the chapter has been very active in promoting the vision of NASI and plans to continue and enhance its activities in that line. So on behalf of the chapter, I welcome you all in the audience to this webinar of Professor Genzel. We all look forward to this exciting lecture. Thank you.
Thank you very much, sir. And we also have with us the President of the National Academy of Sciences, India, Professor Ajoy Khatak. And I request him to say a few words before I invite Professor Genzel. So maybe if you can unmute yourself, sir.
Sir, you are muted.
Can you hear me now?
Yes, sir.
Thank you, Manoj. First of all, I would like to thank Professor Manoj Saxena and Professor Anurag Sharma for organizing this great lecture. And it is indeed a treat for many of us and all the students in our institutes and in the country at large. And maybe there are some participants from outside India. And I'm personally very grateful to Professor Reinhard Genzel for agreeing to give this lecture and enthuse our students in the general area of physics. And I would like to mention that the that the National Academy of Sciences India is the oldest science academy in India. It was established in 1930 by a great astrophysicist by the name of Professor Meghnad Saha, who had done outstanding contributions in astrophysics and also was responsible for setting up many great institutions in our country, and that too in pre-independent India. India became independent in 1947, and he had died at a very early age of 62. And so that is the brief background of National Academy of Sciences, and we are all very proud to be associated with this great academy. With these few words, hand over to you, Manoj, first requesting Professor Genzel to deliver his lecture.
Thank you very much, sir. So he needs no introduction, but as a customary, I'll briefly introduce him to the attendees. So he's born in 1952 in Germany and is one of the directors of the Max Planck Institute for Extraterrestrial Physics, professor in the Graduate School of the University of California, Berkeley, and an honorary professor at the Ludwig Maximilian University, Munich. He's a scientific member of the Max Planck Society and a member of the US National Academy of Sciences. And his research interests include astrophysics of galactic nuclei, star formation, kinematics, and cosmic evolution of galaxies, massive black holes, and the experimental infrared sub-millimeter astronomy. He has received numerous honors and awards, including the Shaw Prize of the Shaw Prize Foundation and the Crawford Prize in Astronomy. In the year 2020, he received the Nobel Prize in Physics jointly with Professor Andrea Ghez for the discovery of a supermassive compact object at the center of our galaxy. With these words, I now invite Professor Genzel to kindly share his screen to deliver his talk.
Right, dear colleagues, very pleased to be here today and talk to you about basically black holes. I mean, the theme of this talk is how in the last approximately 40 years, as you will see, we've been able to tighten up the experimental proof or evidence, you should say, objects were in the universe, and I will tell you how this has come about. Indeed, I should say this talk or this subject I'm talking about is one of great activity right now in physics. Not only the kind of work we're doing, but there's also work in radio in this gravitational waves and seeing the in-spiral of two black holes, for instance, into a bigger single black hole. All of this sort of comes by chance in a way at the same time and 100 years after this theory was invented. Now I start, as you see, by showing you a picture of a forest. Why would I do that? Well, in a way, it's an allegory to astronomy in general. Like going into a forest which you have not seen, which you don't know, and which you would like to explore, astronomers go into their forest, the universe, and walk into it, look at the wonderful trees, look at the flowers, etc., and are awed by the beauty of the universe and the many complex phenomena. That's why astronomy right now, in fact, is one of the most active and exciting fields of physics. Now, physics comes in, of course, because the rules, the laws by which the universe works are embedded in a few physics. And in the case of astronomy, what often happens is that once you walked into your forest for a while and noted down the various phenomena you found, you begin to see, that there are blue flowers and red flowers. And the blue flowers, you find out after a while, occur only on the left side of the path, while the red flowers are on the right side of the path. Now, once this is getting clear and statistically significant, of course, you understand what that is. And that's doing physics. So the talk today, in a way, is part of this kind of an exploration. You start off by detecting objects which you might think might have something to do with these black holes. And then as time goes on, you try to find physical evidence, hard physical evidence, experimental proof that these objects indeed exist. Now, we live in the Milky Way, which is a disk-like system of rotating gas and stars, as you see on the left side. And the right side tells you that this disk is fairly thin. In the center of the disk, there is a thickening, a central bulge, which actually is elongated, so it's more like a bar structure of mostly stars. And then in the surrounding rotating disk, you have also mostly stars these days, and then a sprinkle of interstellar gas, neutral gas, as well as ionized gas. Our sun is about 30,000 years out from the center of the Milky Way. So we are in the outskirts of the Milky Way galaxy. In fact, between two of these spiral arms, so not sitting actually at the peak of one of these spiral arms. Now, 30,000 light years is a distance which you as a human being would say is a long time. It takes light 30,000 years to get from the galactic center to us. Or to put it the other way around, anything we observe in electromagnetic radiation happening in the galactic center actually happened already 30,000 years ago. Now, this might, to us humans, look like a long distance or a long time, but not so really in the universe. The universe is so much larger, and the scales of the universe are not 30,000 light years, but billions of light years. So much, much greater scale. Now, in the computer nowadays, you can go ahead and actually construct a traveling through this system. So here we are in the computer traveling at about 10 to the 12 times the speed of light. And there you see stars as well as these colored nebulae of ionized gas. This is where new stars actually are forming nowadays in the disk of the galaxy. There's another one here. This one is from an explosion of a star. And the Milky Way has about 100 billion stars, 100 billion stars. It's a typical disk galaxy, which is still forming stars, about 2 or 3 stars per year in the entire system, which is about 60,000 light years across. Now, our Milky Way is a typical case of these islands of what we call baryons, normal gas. And between them, the interstellar space is not empty. There's very thin gas, as well as what we call dark matter, which actually dominates the total mass balance of the universe, whilst the content of the normal material in galaxies is only a small fraction of the total. Now, sometimes these galaxies clump together into clusters, as you see here. This is the so-called Virgo cluster. which is about 40 million light years away. Now it turns out that in almost every one of the galaxies you saw in this trouble, in this strip, we now know have a central mass concentration of millions to billions of solar masses, which we now believe to be massive black holes. But let me now start at the beginning of this story 100 years ago, when Albert Einstein designed a new way of describing the physics of gravity, the interaction of masses with their environment. As you well know, this had been done earlier by Newton, and it was understood that if you have a heavy mass and you have another mass, then the smaller mass is attracted by the bigger mass and vice versa. And the smaller mass then can be orbiting around the bigger mass. Einstein expanded this view given new findings. For instance, the finding, as I will discuss in a second, that not only normal masses are affected by this, but also light. Light was not affected by gravity in Newton's theory, but in Einstein's theory it is. Now, the way Einstein described this new theory is basically a geometric picture of space-time, which you see on the right side there, where space-time is curved or distorted by the presence of masses. The more massive objects distorted more, and the less massive objects less. And a motion, an orbit of a smaller mass around the bigger mass is basically a path, which is this dotted blue line along the minimum distance in this space-time, a geodetic curve, such that what was an elliptical orbit, for instance, is now in the space-time a track of the smaller mass in this curved space-time by the bigger one. I said already that in Einstein's theory, in a way, the key new feature is that also light is affected by gravity. If you consider the sun here, and you look at the sun, and behind the sun at some distance is a star, then Newton's theory would have said that light rays coming from the star towards us go on straight lines. That is not so in the theory of general relativity. There, light is affected by gravity, and therefore also light is on a curved geodetic path. Light is bent. In fact, this prediction of Einstein in 1915-16 was put to the test already in 1919 when there was an eclipse, and Eddington and others traveled to the equator near Brazil, and in fact showed that the predicted amount of light bending around the sun of a star field was indeed true, which is why Einstein became so quickly so famous, because of such an astonishing prediction was found to be true. A year after the initial publication of the theory, Karl Schwarzschild, an astronomer also in Berlin, unfortunately at that time already at the Eastern Front in Russia, fighting during the World War I, actually found the first solution of Einstein's theory for a mass distribution which is spherically symmetric. And then the curvature of space-time can be calculated analytically, and you find the so-called metric, which describes very accurately how the space-time will behave in time, as well in the three spatial coordinates, as a function of radius from the central objects given the mass of the object. So once you have the mass, then in this Schwarzschild metric, you can compute the orbit. And remarkable, in this calculation, there is a new quantity which shows up, and that's the so-called event horizon. And that's basically, if you think about it, on the right side there, if you make the mass ever bigger, or you go ever closer with your light ray to the central star, then there will be a point where the light ray will not reach the observer anymore. It will be bent around and in fact then fall into the central object. That is what we would call an event horizon. And then the objects inside of that event horizon radius cannot communicate anymore with the surrounding world. And so that is what we nowadays call a black hole. A black hole is a mass concentration. So it's both this mass itself, as well as a particular radius within which even light cannot escape anymore. And therefore, you have a lack of communication between the inside and the outside. The object in that sense is black. Now, it took another 50, 60 years to explore that theory. In 1963, Roy Kerr, whose picture you see there at the bottom, actually showed that there's another property such a black hole might have, not only mass, it could also rotate and have a spin. And finally, there was a third solution, which does not play a role in my talk, where there can be an electric charge. Now, it was not clear, however, whether such objects might actually occur in nature. These are really weird sort of predictions of theory. Maybe they're just mathematical consequences of a complex mathematical set of equations, but are not realized in nature. And then Roger Penrose showed that actually the particular symmetries, the spherical symmetry or the axial symmetry predicted or assumed by Schwarzschild and Kerr were not necessary for a black hole solution to come about. As long as there is strong enough curvature in the space-time around these objects, you would get a black hole solution. So it's very likely that if such a state of matter occurs, you might have these objects. So does no light escape from such a black hole?
Manoj, the slides are not changing. The slides are not changing.
That's correct.
Yes.
That's correct. I'm showing just the same slide at the moment. Okay.
Sorry.
The question is whether no light is escaping truly. Well, there's the story of the last one on this, of the man on the left side, on the right side, and that's Stephen Hawking, who passed away just a few years ago. And he actually showed that if you consider the quantum nature of these black holes, there might be, in fact, through the uncertainty principle, escaping of a small amount of radiation from through the event horizon. We have not seen that yet, and it will be probably very, very difficult to see it, but that's another prediction of the theory. Now, of course, we are familiar with gravity ourselves, and we know that if we jump up from the Earth, we don't get very far because gravity pulls us back. And if again go to the sun and you put a rocket on the surface of the sun, then that rocket needs quite a speed of about 600 kilometers per second. On the Earth, that's about 11 kilometers per second, to leave the surface of the sun and escape, so to speak, into interstellar space. Now, that escape speed of 600 kilometers per second is given as a result of the the mass of the sun and its size. Now, in your mind, you could now change either of these quantities. Let's leave the mass alone and make the sun smaller. If you make it as small as 3 kilometers, then you can calculate that that escape speed of the rocket is 300,000 kilometers per second, the speed of light. So that's what I basically already told you before. You can have a situation where gravity is so strong that this event horizon then makes the objects invisible. All of the mass then is predicted by the theory to reside in a singularity, in a point at the very center. What a weird prediction. Very, very, very weird prediction that there'll be a singularity of infinite density where all the mass is and light cannot escape. Now, if such objects would exist in the universe, how would you find them if you can't see radiation? Well, the answer is they are having the same effect on their surroundings in terms of their gravity as an object with one solar mass but visible would be. So if you think of a black hole of one solar mass and you put the solar system and its planet around it, then they would orbit around this object just like in Newton or Kepler, which means that the innermost planets, Mercury, Venus, move faster than the outer planets like Jupiter and Uranus and so forth. And the speed of the orbit around the central object goes like 1 over the square root of the distance from the center. So it's that indirect way how we can make gravity visible and how we can make black holes visible, even if we don't see radiation from it. As I already indicated, but I won't say much more about it until the very end. Another way of sensing the gravity is through gravitational waves, because the fact that, this motion of Mercury is on a bent orbit means that gravitational waves of, in this case, small intensity are emitted and in principle can be sensed far away. Now, in 1963, the radio astronomy community in the United Kingdom discovered a new class of radio sources. They are called quasars. So if you look at these objects in the radio band, they're very intense radiation sources, variable emitters. If you look at it in the optical, like here, you look like a star, a faint star. This radio source 3C273 is an object which obviously you wouldn't have noticed as very special in the optical because it's a 15th magnitude star. But in the radio band, it's very, very intense. Now, Martin Schmidt was informed about this, and he took the big Mount Palomar optical telescope and looked at this object 3C273 in the optical bands and looked at its spectrum, its optical spectrum. And he saw that there were spectral emission lines in this spectrum with characteristic wavelength ratios, which are very well known to everyone due to hydrogen, helium, neon, and other elements. But they were all redshifted relative to the laboratory frame by 16%. So you see this number Z equals 0.16. Now, Hubble had already shown in the 1930s that the universe is expanding and that the further away an object is from us, the faster the motion is, and therefore the Doppler redshift increases with distance. So this Hubble law can be used to infer for a 16% redshift a distance of about 2.4 billion light years. In 1963, that was a sensation because nobody had at that time seen objects that far away. Nowadays, we we know objects much, much further away. In fact, almost as large as the entire lifetime of the universe. Now, if you take this large distance, you can compute how much this faint optical emission actually amounts to in terms of total radiation. And it turns out it's about 1,000 times as luminous as the entire Milky Way with its 100 billion stars. So in the decade after Martin Schmidt's discovery, many such quasars were found, ever more massive, ever further away, and ever more luminous. And so clearly, people were thinking, how could we possibly understand how they produce so much energy? Now, the idea coming in the end through a number of people, Donald Lindenbell, Martin Rees, Rashid Sunyaev, and Roger Blandford, is that if you have a black hole, it's black inside this event horizon, as I described to you. But if you have material falling onto the object, then the gas, for instance, then the material, as it is attracted by and falling into the black hole, and before it enters the event horizon, gets ever hotter because gravitational energy can be converted into heat, and the heat can be converted into radiation. So in fact, just at or near the event horizon, you can convert between 10 and 40% of the rest mass energy of a particle into radiation. So that's about 100 times or several hundred times more efficient in terms of radiation production than fusion of hydrogen into helium. So that paradigm was created in the mid-60s, that there are indeed objects as predicted by the theory of general relativity, black holes, that they are very, very massive objects. I'm not mentioning here that at about the same time, also another type of object was found, which might be black holes, but much less mass, of about 10 solar mass, which we call stellar black holes. These very massive objects, or supermassive black holes, reside in the centers of big galaxies. And we know now, as I mentioned at the beginning of my talk, that such quasars or such massive black holes appear to be residing in almost every center of a Milky Way. So the formation of galaxies and their evolution and growth, and the formation and evolution of massive black holes, at least in this theoretical explanation, are closely coupled. But is the theoretical explanation correct? That's the question. And quasars are much too far away to make any of the tests which I already indicated to you. But Lindenbell and Rees said, well, actually, if every galaxy has a black hole, so might our own. So if you go and observe our very close by central region of our galaxy, then you could see whether there is a large mass there. You could see that from the motion of this neighboring gas and stellar particles, so to speak. And that is exactly where our work has come in. Now, this is a modern picture of the central region of our Milky Way on a scale of a few light years. Now, you can't do that in the optical because there is a lot of dust, interstellar dust in front of the galactic center. So you have to go to the infrared band a few times the wavelength of optical radiation. And see that there's a very dense star cluster in the center of our Milky Way, about 1 million times denser than the solar neighborhood. So clearly, these are our test particles, the stars, and there's also a gas in the central region. And the radio astronomers, in fact, showed that in the center of the star cluster is a very compact radio source, very intense, small radio source with a size at 1 millimeter wavelength of only 40 micro arc second. A micro arc second, 10 micro arc second on the moon is about one centimeter. So this is a very, very small object, but very intensely radiating, a bit like a micro quasar, if you like. And so many people immediately felt, oh, maybe that's our candidate where there might be a black hole. So how would you test that? Well, you should measure the motions of objects surrounding this region. Now, you have to do that in the infrared, and initially it was done with Doppler motions of gas, ionized gas here in pink, and neutral gas in green. Now, Charles Townes, who had obtained the Nobel Prize for the invention of the maser and the laser, had moved to Berkeley, California in the 1960s and started a new career as an experimental astronomer. And he and his group built the first spectrometers to look at infrared waves. And so they could, in fact, look at the spectral line of neon and measure the motions of this ionized gas in pink there. I joined his group in the late 1970s, early 1980s. And so we then started to measure the motions of the gas. So then when you measure the motions of the gas as a function of radius from the center of Sagittarius star, what you find is that you go far away, there's a large mass, you go inside, then the mass on the vertical axis drops. You go further in, it drops further, but then inside of about three light years or so, that's 1 arc minute roughly, the mass doesn't change anymore. It stays roughly constant at a few million solar mass. So by, I would say, the mid-1980s, our group in Berkeley was fairly convinced that we had found the first true proof of a massive black hole of a few million solar masses, just like the theorists had predicted for these quasars. I said there's not a very low luminosity object, so clearly there's not all that much accretion going on, but still the mass it seems to be there. Not many people believed us, though. We wrote a Nature paper about this at the time. People didn't really believe us. Why? Well, distance of a few light years is about 1 million times the event horizon size of a million solar mass black hole. So you're still very, very far away from where general relativity would expect the action should be. So it's possible that what we're looking at is a very compact cluster of stars. For instance, at that time, neutron stars had been discovered. So if you put about 1 million neutron stars into this central region, we would basically observe the same thing. So how do you make progress? Well, obviously, one thing you want to do is to measure more precisely, and you don't want to measure only the Doppler motion, you want to measure the motion on the sky, and you want to actually not only use gas, you want to use also stars, because the stars are much better tracers of gravity than gas, which you can push around with magnetic fields and winds and so forth. So the plan, when I then moved here to Germany as a director of a new group, was to build new equipment in the infrared to measure the motions of stars. And let me just take a few minutes to point out that, in fact, the development of new technologies is indeed the key thing in modern astronomy, just like in many other fields. We had to develop very low noise infrared imaging detectors. Your CCD, which you have in your cameras, won't do. And infrared imaging detectors initially were not available. The American military had them to check out Russian rockets. But it took quite a while to build imaging detectors, ever better quality. The next problem is when you look with your telescope at a distant star, the light has to go through the atmosphere. And the atmosphere refracts the light. The winds in the atmosphere distort these refracted light waves. And what arrives at the telescope then makes an image which is distorted and unsharp, independent of the size of the telescope. So you cannot get very sharp images. And the solution technically to overcome that is to measure these distortions and then undo them with this deformable mirror and then bend the light waves straight again. That's called adaptive optics. And it's nowadays the standard technique for all big telescopes. In fact, the next generation of 30, 40 meter telescopes won't even work without adaptive optics. But this is now a technique which we know how to do. You have to have very fast computers. So computing is an essential thing. You also want to do spectroscopy across the field and not just like with the grading spectrometer at a point or along a line. And then finally, sometimes when you do your adaptive optics work, the star which you use to make the images sharp through adaptive optics, which is what you see on the left side, is too faint to make the analysis. So you have to actually make your stars. And we do that by sending laser beams in the outer atmosphere. At 90-kilometer altitude, there is a layer where meteorites, which come into the Earth's atmosphere, make a rain of destroyed material, including sodium. And that sodium gas we can excite with the sodium D laser, which you see there, this yellow beam, and a backscattering of that beam we can then use to sense the distortions of the Earth's atmosphere. So the point I'm making is that all what happened over these 40 years is ever improvement of the technologies in factors of about 1 million in sensitivity, several thousand in angular resolution, et cetera, et cetera. So really without that, we could not have gotten the kind of results we have now. Now, this all started then in the 1990s with the first measurements. We had started this in Chile with the European Southern Observatory on a 4-meter class telescope. At the same time, another group joined, the Hunt, Andrea Guess at Caltech, and they could use immediately a bigger telescope, the Keck telescope, a 10-meter class telescope. And so we both groups then started measuring the motions of stars. And here in this picture, I show you the result after about 3 years of measurement in 3 different colors. So red is year 1, green is year 2, and blue is year 3. The cross is the position of Sag A star, that radio source. And the circle, the green circle, denotes about a light month. So here we are now already on a fairly small scale. And you can see that there's a star which obviously moves because you see the images of the 3 years, the 3 colors clearly is separated. In fact, moving at about 100 times the speed of the Earth around the sun. And so if you calculate what the mass is implied here at a few light days away from the radio source, what you find is a few million solar masses. It's the same mass we had identified a decade earlier with these gas motions, although on much larger scales. It's also clear that these stars, this mass must be compact, because if you look at the other stars, the further away you go from the green cross, the less color. That's Kepler's laws, right? The further away from the center you are, the lower the velocity due to the distortion of the space-time. And so clearly this mass of a few million solar mass must now be included within about 10 to the 5 times Schwarzschild's radius. So it's about a factor 10 inward from where we had. Is that good enough? No, not really. Although people were then in the end 90s beginning to take this very seriously. It's not good enough because we're still not far enough in. And also, this is a statistical measurement because we don't know, of course, where that star is along the line of sight. What you really would like to have is an orbit, like the orbit of the planet around the sun. So you want to see not just a velocity, but an orbit. Now that seems, very, very impossible for the outer stars there because their orbital periods are hundreds of years. But then if the star is close enough, then you might be lucky. And indeed, we were lucky that this star, which you see there, is on a highly elliptical orbit, which then in 2002 turned around Sagittarius star and went back out again. At that point in 2002, the star was a mere 15 light hours away from the radio source and moved with about 2.5% the speed of light. 17 light hours, that's about 1,000 or 1,400 times the event horizon of a 4 million solar mass black hole. So that's really impressive. And so clearly that is the point in 2002 when many, including the physics community, felt that this experiment had shown, the likelihood that this the idea of a massive black hole in galaxy centers is indeed correct. But let me ask again, must it be so? In order to make these inferences, of course, we are adopting the assumption that general relativity is correct. In the mass and size regime where we are measuring, that has never been tested. General relativity has been tested in the laboratory and in the solar system, but not on these extreme scales and in the relativistic regime. But the star, as you see, has an orbital period of only 16 years. So in 2002, we knew it'll come back in 16 years to the same position. And then if we have still better equipment, better measurement techniques, then we could test general relativity for the first time, like in a laboratory, turn the problem around. Now in these 16 years, both groups measured many other stars. And here we are in the forest again and see the beauty of the phenomena. So clearly this black hole, the central object, is surrounded by stars which orbiting it on highly elliptical orbits. I don't have time to discuss that this by itself is a riddle which we still have not fully understood how stars can come so close. But let me come back now to the tests of general relativity and what we've done in the last few years. I said we wanted to measure still better and use the next Kerr approach of that star S2 in 2018 to test general relativity. How can we do better? We have 8-meter class telescopes now available on the Paranal Mountain in Chile, And the wonderful thing is we have four 8-meter class telescopes. The measurements which I've shown so far were obtained with one of them, the rightmost one. But actually, if you combine the light of the four telescopes together through a so-called interferometer, then you can construct the equivalent in resolution of a 150-meter diameter telescope. That's just the distance, the largest distance between two of these telescopes. And so we built, under the leadership of one of my senior scientists and a European team, a very complex but now very, very successful instrument called Gravity, which combines the light of the four telescopes and achieves a resolution of milli-arcsecond. So that's a factor 20 times better than what we had before. And we can pinpoint the positions of stars to somewhere between 20 and 100 micro-arcseconds. So this is really spectacular precision, so that we can see the motions of stars on a daily basis, as you will see in a second. So this resolution really, in terms of astrometry, gives us the resolution like a euro cent coin on the moon, so we can see very precisely. So let me just go through how that happened. So when we started with our measurements in the 90s, the central star cluster looked like this. When we then developed adaptive optics, we then were able to resolve this cluster into much more compact and also fainter stars, as these stars, which I've talked about, have these wonderful orbits. Now, if you look at this central region again now, and now go very close to the position of Sagittarius star, which is that cross in the center, then with gravity, we can look at this region and resolve the central 100 milli-arcsecond around the star. This is in fact a picture from last summer, where you see the Sagittarius star itself, which also radiates, as well as four stars. And these four stars are all moving, and we can see these movements and within half a year deduce orbits. So that tells you, if you have this fantastic precision, you can really get highly precise measurements of the space-time surrounding Sagittarius star. And as I said, when you are close to the position, you can see the motions, in fact, from night to night, not from month to month or year to year as before, but from night to night with high precision. And then indeed, it's possible to test general relativity, and we've done that now. And general relativity has passed these tests with flying colors again. The first such effect we are expected to see and did see is the so-called gravitational redshift. So if you have a star moving near a heavy mass and then shines light towards us, then the light has to climb out of the gravitational potential towards us. And the closer it is, the more that that redshift is significant. And if you in this plot there on the lower left denote the Newton orbit as a horizontal gray line, then general relativity would predict the red line. You clearly see that the measurements in these circles and cyan color, the measurements clearly follow general relativity. So this is a highly significant test of the gravitational redshift. The next effect by general relativity is the so-called Schwarzschild precession. In Newton, if you have a central mass and you have another mass orbiting it, and there's nothing around that, and the second body is bound, then the motion is an ellipse or a circle. and that is stationary in space. That's not true in general relativity. In general relativity, the orbit precesses because of two effects. The first one is because of the mass, and it's a prograde precession, which in the case of that star is 2. It's about 12 arc minutes per orbit. And also, if the black hole has spin, then it also precesses. And we've seen the Schwarzschild precession now with high accuracy. Again, the Newton orbit there in the bottom central diagram is the horizontal gray line, and red is what general relativity would predict. And the red and cyan circles is what we've measured. So clearly, you've seen the Schwarzschild precession. By the way, that tells us indeed that the object must be a single mass. So it's not a double mass. Like, for instance, it could have been a binary black hole. That we can exclude. We can also exclude that there is much mass, significant amount of mass around the black hole. It's really a single point. Finally, we can actually look at Sergei star itself. It emits in the infrared, as I mentioned to you. And from time to time, it becomes very bright. We call that flaring. This is synchrotron emission just outside of the event horizon. And when we measure the positions of these bright spots, then it looks as if there is sort of a loop motion around the event horizon at about 30% the speed of light, and about 5-6 times the event horizon size. And so if you convert that into a mass, that's exactly what you would expect for a 4 million solar mass black hole. So we can actually now see the motion and measure the space-time all the way down into the relativistic limit in the galactic center. So after 40 years, we've come a long way. We've been able to measure the mass, which is the vertical axis, as a function of radius through different techniques, starting 40 years ago at around 1 million times the black hole event horizon size, and showing that this dominance of a point's mass, which in this case is a flat horizontal distribution, to go inward to the innermost stars, S2, and our colleagues at UCLA find the same thing. And now we can even trace this all the way to the event horizon. And as I mentioned, we can show that on the scale of the stars, like S2, there's very little else in terms of mass. It really does appear to be a central single black hole. So the question, of course, is, are we done? The question I asked several times. No, we are not done, because we have not yet measured the spin. And we know that the spin of the black hole is the second quantity we need. And once we have the spin, then we can make the ultimate test in general relativity, which is the so-called testing the so-called no-hair theorem. That basically says that once you have the spin in the mass, then all other properties, for instance, the quadrupole moment and the octupole moment and so forth, all can be predicted from these two first quantities. The black hole has no hair, no wheels, no extensions, nothing which is more complicated than basically can be described by these two numbers. And so that's something we would like to, of course, do in the next years. Whether that will happen during my lifetime as an active scientist, I don't know. But many people are interested, of course, in these questions. We are building now an upgrade of this gravity machine to be still more powerful and precise. The radio astronomers are combining radio telescopes across the entire globe to image the innermost region and see the curvature of the photon orbits. in about 6 years from now, we hope to have a 30 and 40 meter class telescope, a so-called extremely large telescope, and we are building the first camera for it. So that might give us the chance to measure still fainter stars. We'll put a very, very complicated detection laser interferometer into space, which can see the inspiral of massive black holes or of a stellar black hole into a massive black hole. And then a whole slew of interesting questions can be solved. The spin of the black hole, testing the no-Hair theorem, understanding tidal disruption, looking for intermediate mass black holes, not these supermassive black holes, testing the possibilities of having binary black holes. And finally, of course, to ask the question, when and how the black holes actually form, at what time in the history of the universe, and how they grew. So this is a very active field of modern astronomy, and I hope I've been able to give you a bit of a insight and recording of what I've been doing for 40 years.
Thank you very much, Professor Genzel, for enlightening us about your 40 years of journey and your significant contributions and the contributions which have been made by other experts in this particular area. So there are a few questions which I can see. There are plenty of them, but due to paucity of time, I'll be taking some selective questions from the chat. Do I have the permission? Can I take up certain questions? Yeah. Okay, fine, sure. Okay, I'll take up the first one. Are the supermassive black holes the reason why the center of galaxies glow?
Glow.
Yeah.
Well, they glow also by the stellar concentrations there. So even, I mean, our galactic center, as I said, does have a massive black hole in there, but it's not very bright. I mean, it's there, but you can see it, and it sometimes is a little brighter. And in fact, there were periods in the past when it was much, much brighter. You know that. But the stars in the galactic center are bright enough because there's so many of them. So, but indeed, if you have a black hole which is creating near the maximum, so-called Eddington limit, then that's about the brightest source of radiation you can think
of. Okay, I'll take up the next one. For the fabric of space and time, do we consider that all bodies are on the same plane, that is, on the plane of fabric? And if not, then how do bodies having different spatial arrangements experience gravity as per general theory of relativity?
I'm not quite sure I understand the question. I mean, first of all, the picture is that in our universe, you have 3 spatial dimensions, and then, of course, time as the 4th. If that's correct, then basically any mass can have a orbit in whatever orientation through the space-time. Now, if you then have a massive black hole, as I said, or any dominant mass in general, and then you put another object around it, then indeed the preferred motion, if you have no further disturbance, is a plane. That's correct. If the object is a black hole which is spinning, then that plane actually wobbles. Okay, that's the precession. But other than that, objects move in 3 dimensions.
Okay. I'll take up the next one. Assume that we have a super dense star. Is it possible to find an exact solution of the Einstein field equation of such a star, considering a star is radiating and charged at the same time?
Yeah, of course. I mean, that's exactly what the Einstein equations would give you if you construct a stellar source with fusion as a radiation source, and then its gravity, and you let it evolve. If that star becomes denser than or becomes smaller than the event horizon, it will collapse to a black hole. Okay, and so you can calculate that both analytically as well as numerically. That in fact, that is what Roger Penrose in the end got the Nobel Prize together with me and Andrea Ghez for, that he showed that indeed a star which is sufficiently compact and massive must collapse to a black hole.
Okay. There are plenty of questions, but I'll only take up the last three now. There are beliefs among other astrophysicists that the concept of black holes can be replaced by photon sphere, and the gravitational waves can be the reason of radiation pressure. So how can we say with confidence that we have discovered the black holes and not something like photon sphere?
I don't know that, what you're talking about.
Okay.
As photon, I mean, what certainly is correct is that if you, in fact, I described that if you have a black hole, then the photons moving in space-time around it will be on curved trajectories. That's very clear. And so there will be an innermost radius, which we call the photon orbit, just like in the case of a particle. It's still further in, but it's a defined radius, which in the case of a Schwarzschild, a non-rotating black hole, is 1.5 times the event horizon size. And then on that orbit, the photon will go on in circles. Inside of that photon orbit, even the photons will fall into the black hole. There's nothing they can do about it. So you can certainly postulate that there's a high density of photons surrounding a black hole, but you cannot construct 4 million solar mass object at the photon orbit, because that would collapse into a black hole again. So it's inevitable.
Okay, I'll take up the second last question. It's more related to the institutes you have been associated with it. Well, there are two Max Planck Institute of Astrophysics and Physics, both in Germany. What different operations and activities are carried out in the third one? And how is it different from the others in terms of the research work?
Okay, look, the Max Planck Society is a governmentally sponsored institution to do basic research in all kinds of fields. And within the MPG, we have about 87 or so institutes, separate institutes, 4 or 5 of which are doing one form of astrophysics or another. Our institute is devoted nowadays to mostly experimental work on the ground and in space at wavelengths which go from gamma rays to radio, as I mentioned in the beginning of the talk. Our neighboring institute over there is called Max Planck Institute for Astrophysics. So they are doing exclusively theoretical work, both numerical simulations as well as analytical in various parts of astrophysics. So of course, that is closely connected to the experimental work, because our observations are guided after all, and they need interpretation. It's largely optical astronomy in Heidelberg. And then the fifth one is doing largely gravitational gravitational waves. And others, in other institutes, there is little bits and pieces of astrophysical research. And then, of course, there's also the connection to particle physics in the sense of a very high energy gamma rays and so forth. So in total, I would say about 10 of the activities of the Max Planck Society are in astrophysics and astroparticle physics. So it's a big field.
Okay, okay. I'll take up the last one. How can we measure the spin of a black hole? This, I think, from one of the students, I suppose. Yeah.
Right. So spin of the black hole now means that the black hole has actually a preferred direction, right? Because it spins around its rotation axis. And that means that the space-time near the event horizon is getting dragged along with this rotating black hole. Now, if you think of a particle or a star, which is now rotating, it sees the space-time moving away or towards it. And therefore the motion, the planar direction of the star or the particle is changing with time. So it's wobbling, okay, it's processing around the rotation of the black hole. So that's something we would like to see. So in that case, if the star S2 would be a little further in, we might have been able to actually see that with our measurements. Unfortunately, it's a little too far out in the so-called lens steering precession, which you would measure, is too small for our accuracy.
Thank you very much. I now request Professor Ajoy Ghatak and Professor Anurag Sharma to kindly give some concluding remarks.
As you know, that's always wanted Manish to be here. That's why, yeah. So, hello.
Yeah, we can hear you, sir.
Yeah, I think there's nothing much to add. I mean, it was a great lecture that we all enjoyed, and there's so many answers, so many questions raised that tells you really excited that imagination. So really, I would like to thank Professor Genzel for this wonderful lecture, and we hope that we'll have some other time again for a slightly different topic, maybe. Yeah. Thank you very much.
Okay, thank you, and thank you for listening to me.
Yeah.
Thank you very much, sir.
Okay.
And I would like to thank all the attendees for being there with us. So I seek your permission to close the session for today.
Okay, goodbye.
Thank you. Okay.
Good.
Thank you.
Take
Thank
care.
you.